Last lecture we took a walk through the swamp and derived the nonlinear filter for hidden Markov models. And I did, so I'll upload my notes later tonight. I went through and I checked them this morning just to see if they really were suitable for public distribution. I think they're okay. So it's a beautiful concept. You take a partially observed Markov model, and by going from a finite state space Markov model to this infinite dimensional belief state, you make the whole problem fully observed, and also you get this beautiful structure that the value function is suddenly convex or concave as a function of this belief state. But of course, it's way out there. It's a lot like Shannon's information theory. While speaking to you, I mean the idea that you get this ideal of what's the optimal thing to do. You get this beautiful structure, but computationally it's almost worthless. And it takes somebody else to come along and come with computational tools to make it useful. And so far there hasn't been the brilliance and control that there has been in information theory. In information theory, I don't know as much about it as some people here, but using linear algebra techniques, people are able to meet the beautiful Shannon theoretic limits on information transmission through some crazy ideas that were a million miles from Shannon's original formulation. Here we have this beautiful theory that says I can say that my belief I've got some I of t, I should say plus 1. I've got this beautiful theory that says I take this partially observed process where I start with x of t. I start with a Markov chain on d states. I go to this infinite dimensional thing, but it's fully observed. I can choose my control based on observing this information state at time t. And my value function is a concave function. So it's this beautiful structure. But the computational tools, I'd say right now, are almost zero. It's almost all salesmanship, if you ask me. And you can make a lot of money consulting, though. I mean, people make millions taking this to Wall Street. And there are success stories. It's still a very primitive area. I think it definitely deserves a lot more research. So the place where this works really well is if you go to a Gaussian setting. So today, let's go and forget the finite dimensional setting. Let's look at the Kalman filter. Okay? So it's exactly the same problem. I again want to work out the estimates, state estimates. My two goals before was what I want to compute the conditional distributions of the state given my observations y. And control, I want to apply this to control. So the beautiful thing here is I got a fully observed problem, so I know that u star of t is going to be some function of my state, Yes. But in the linear case, what happens? Why is it so nice? Linear quadratic Gaussian. So before we do anything, let's think about this. Why should this be nice? By the way, the notation here looks a little bit funky when compared to my MDP notation. I've got y of t and a wt plus 1. This is just what you'd see in a book like Anderson and Moore. Which is probably the best reference for this material. So this is really fragile now. So remember when I talked about control for the fully observed case, I wanted n and w to be IID. I said I don't care about the distributions, and that was it really. But now it's got to be Gaussian, and I'll assume zero mean. So I'll assume the system noise and the observation noise are independent. They're both IID. Gaussian zero mean. So why is this so important? I want you to tell me. Got a linear system, it's given by Gaussian noise, and I'd like to estimate x based on my my measurements of the output and the input as well. So what makes this so special? Before I was fixated on having a finite state space so I could have a computationally tractable algorithm. Why is it that if I have a Gaussian assumption, it's all computationally tractable?
Easy to integrate.
What's that?
It's easy to integrate.
Yeah, but then that is true. But then I could take n to be, say, a two-sided exponential, maybe. That'd be even easy to integrate, or a uniform distribution, which might be easy as well. So it may be true, but yeah.
X of t plus 1 and y of t are both going to be Gaussian, so you can just use the first two moments to characterize the whole distribution.
Yeah, and that's the fact that Gaussian distributions are characterized by their first and second moment. So the conditional distribution is going to be Gaussian. So I hate these things. I thought I got new ones. So for 1, so referring to the same 1, so this distribution, condition on the past, is going to be Gaussian with some mean, which I could denote x hat of t, and some covariance matrix, which I'll denote sigma hat t given t. And I'll also use the same consistent notation. X hat of t or x hat t given t. I'll use the same notation. Okay? So that's just a fact when you have a linear system, everything's Gaussian, and then you find the conditional distribution is Gaussian. So that's why 1 is tractable, because that's a matrix, that's a vector, it's all something that you can fit in a five-dimensional world. That's the first thing. The second thing, the control. This is really, really critical. This is what makes it so easy. The fact that I don't have to explore. In a lot of problems, I have to put in some crazy input to jiggle the system to learn about it. You know? And here I don't. No matter what control I do, this covariance here is going to be the same. And that's what makes control easy. You know? And I'll explain that in a bit. So it's valuable for control, provided we have quadratic cost. Why is that? Well, let's look at the finite horizon cost criterion. Okay, so take the conventions we've had before. You know, we've got quadratic in x, quadratic in u, and look at this thing that we've looked at before. So remember we were able to write this down as some sort of norm. So this is, if you could go back to your notes, we were able to write that for any input u, we were able to write this as something like this plus the optimal value function. Okay? Now there's a t here, there's a certain norm, a weighted norm. And what I mean is like the norm of z. So remember this matrix here, HT, it was, just go back to your notes. Put this in big parentheses here. So go back to your notes, we showed this. We showed that we could look at the finite horizon cost, it was some error term plus this, and that's why I said we should set u equal to k times x. And actually it should be a plus sign, shouldn't it? Because it was a minus. Because we had u equals minus k was the optimal policy, right? All right. So get out your colored pen. Not very colored, is it? Get out your crappy purple, purple pen. What I want to do is I want to add and subtract x hat. Okay. Now this covariance here. covariance here is the conditional expectation of x tilde x tilde transpose given the observations. And this covariance matrix evolves on its own according to nothing. It just buzzes around. So what I can do is I'm going to get a covariance term right there. A little bit of algebra. A little bit of algebra, I can write this as u plus kx hat, and then I'll have the deviation term, the x minus x hat. That's all. And then plus the error it's just that. All I'm doing here is I'm saying the expectation of x tilde t, ht x tilde t, that turns out to be equal to the trace So a little bit of linear algebra you should all know. It's a beautiful fact that if you take the trace of AB, it's the same as a trace. I mean, if you take a dot product, you write it as a trace, just by reversing the vectors. And I can take the HT outside, and what I get is my sigma t, which turns out to be a completely deterministic object. But this is just equal to the trace of HT sigma t. So that's what I've done here, getting this. And this is independent of control. That's the thing. So exploration doesn't help me. I can't reduce the covariance by putting in a crazy input. So therefore, what's the optimal control? The same as before. I just replace, I have u equals minus kx hat instead of this. And this is called the principle of superposition. And many would say, well, of course, what the hell? What else are you going to do with x hat of t? Of course, I could pretend it's a real state. Well, sometimes that's going to kill you. I'll give an example, probably next time, probably on Friday, where if you did that, it would just blow up. It wouldn't work at all. This is so fragile, it's unbelievable. You change anything in this problem, it's not true. You make it non-Gaussian, it's not true. You let the parameters in the model change with time, it's not true. Anything you change in this problem, it's not true. So the principle of superposition is really, really, really fragile. Okay? And often, we will, as engineers, sometimes we'll pretend our state estimates are a reality, and we'll do this, and sometimes it'll work and sometimes it won't. Okay? For the LQG case, you can prove something. Okay? And the proof is pretty fast. We just have to verify this. Why? And that's all we have to do. And so in order to prove that this doesn't depend on you, I have to walk through the swamps again and derive the Kalman filter. And I want to do this in broad strokes. I'm not going to go through every detail, but you need to see it at least once. So last couple of lectures, we derived the nonlinear filter. It was just Bayes' rule. When we derive the Kalman filter, it's just some least squares. It's basically the projection theorem. Question? So the policy is the same. Of course, the cost goes way up. It doesn't depend on x, but it does mean that the minimal cost here, if you minimize overall admissible controls, so long depend on the observations, it goes up by that much. Okay. So, what do we need to know? I've got a list here of everything you need to know. We have these zero mean Gaussian vectors. It's crucial to zero mean in the Gaussian. And number one, so if the expectation of x, y transpose, so x is a column vector, y is a row vector, so that's a matrix. So that's the covariance matrix. If that's zero, then they're independent. So I'll use this funny symbol here for independence. It's sort of like orthogonal, but that's a useful fact. That independence is so simple. This means this strong uncorrelated assumption. Okay, so I'll write, if I really have to be pedantic, I'll write sigma y y. But sigma y is the covariance matrix. If that's positive definite, if that's a matrix, so when greater than zero means it's positive definite, then I can compute the conditional mean. So I'm not going to, you can set this up in a vector space setting, and this formula, the conditional mean of x given y, is this linear function of the elements of y. And that can be interpreted as an L2 projection, just like that is the L2 projection of my fingertip onto this desk, okay? So I mean, that's something, I don't know, I wish I knew you all knew, but if you didn't, it's okay, you don't need to know. So it's a projection thing. That's a dot product of x and y, and that's a normalization. 3. I haven't mentioned z yet. Suppose that the correlation between y and z is there, which means that y and z are independent. Then another incredibly useful fact so think of it as an update rule. I've already computed the conditional expectation of x given y. Now I've got some more information. I have z. Well, you just add it up. Do you see how lovely this is? I mean, you know, it's just the fact that you can just do these trivial things and compute everything is why the Kalman filter works. I'm going to call that I, because this is a whole bunch of different stuff. Secondly, the covariance of this. These also sum up. Just one, let me write this down. Somebody say something? Okay, excuse me. No? It's hearing voices again. And finally, look at the error. So I got this extra bit of information through z. I know how to update my estimates. I know how to update the covariance. What I'd really be interested in is the covariance of the error, x minus x hat. And how does that get updated? What should it be? Well, my error better go down. So there better be a minus sign. And it's exactly my new information. Is that right? Oh, they're independent, that's right. So it's the size of my new information. Is how much my covariance moves down. Okay, so you get this by playing around with this again, adding, subtracting terms. All right, so obviously this is meant to be applying the recursive algorithm, and if I don't finish in 20 minutes, I just won't finish, because it's just not, you know, it's like now it's just a matter of plugging these things in. And do you all have this written down really nicely in your notes? If not, just finish it up. Because we just want to go back to this. I want to be able to say 3 double I, and you all tell me what to do, okay? Ideally, I'd go like that, and this would go in that forward. Right? And if it's a mistake, I don't care. I'm going to apply it anyway. We'll get the right algorithm. Okay, let's do it. Okay, let's go to our algorithm. So, I hope. I refuse to do this without a cheat sheet. All right, so first of all, we've got to do something. We've got throughout these steps, I assumed I had zero mean Gaussian random variable. And we don't have that. You know, my input might be trying to regulate this airplane to 30,000 feet. So when I want to decompose into something that's driven by noise and something that's driven by the input. We assume that the initial mean is given, and this just is some state space model that evolves on its own, and we know it. This is an observed process. So x of 0 is assumed to be Gaussian. And if you subtract off its mean, that's a mean 0 Gaussian random variable. Okay? And so I'm assuming this is 0 mean as well. So this is a Gaussian 0 mean process. And that's that. So the idea is that I'll subtract off the things that I know. Now I don't want to carry around xn of t all the time, so we might as well just assume it's 0 altogether. You know? To simplify the notation, just pretend there was no input to start with. See the justification here? You know, basically, I can take, I can subtract this known quantity, and then I get a 0 mean process. So why not just, to simplify notation and just look at the model without the input. So if I set u equal to 0 and I assume that the initial mean is 0, then I'm just saying that xn equals x. So this is my new model. You happy with that? You're happy? Okay. You're happy. That's all I care about. All right. So now we can derive this. So that's my model. So there's our model, and remember that n is independent of W. So the state noise and the observation noise are independent. Their ID, their Gaussian, and stuff. I've just got, all I've done is I've gotten rid of the input and made everything zero mean. What are you going to do? So I want to work out the conditional mean. That's the first thing. And all I've done is I've separated this into two parts. Everything up to time t plus what happened at t plus 1. So remember, this is the history of all the observations up to time t. And there's no input now. It's just that. Okay. Yes? All right. And what I want to do is rewrite this a little bit. What I'm going to do is I'm going to replace y of t with the innovations. The innovations is defined to be y of t plus 1 minus your prediction of it at time t. That's just the definition of the innovations. Okay? You'll find this in filtering theory all the time. It's the new information from your latest observation. Okay? And this is the same thing, because given all of this, I can get this, and given all of this, I get this. There's just a one-to-one mapping between the two. The key is that this is orthogonal to the past y's, so it's independent. So because this is the error based on all the past informations, we know this is true, which means that the innovation is independent of all the past y's. That's the crucial thing. That's why innovation is brought in. And so now we can use our rules. Okay. Now, somebody look up which rule this is. By rule, I guess it's fact 3, is it? It's the estimate given this plus the estimate given this. Oh, wait, yeah. Okay, so when we condition on two independent objects, you get the sum of the estimates. And so now we got to go through and work out what these are. Luckily, they're not that bad. I mean, take a look. What's this? None of you leave this room until you tell me. What's the estimate of xt plus 1 given the observations up to time t based on that formula? Remember,
A times the previous estimate.
yeah. This is independent of the past. this, we got to break out our formulas. And let's write it down. What the hell? What I say it was sigma xc sigma c inverse c. Is that rule number something or other? Which one's that? 2? Is it 2?
Yeah.
Is that right? I think that's right. Okay. So that looks scary, you know. I mean, it's, you know, what on earth are these objects? So. And but that's no good, it turns out. So it's easy to work in deviations. So I'm going to look at the deviation between xt plus 1 and what you thought was going to be a time t, conditional mean. And this is something in yt. And so its mean given something independent of yt. The mean of this, given some independent of yt, is 0. So even though what I wrote here is correct, I don't like it. I'd much rather work with the deviation term. And notation. It's much easier to write like this. Just to avoid confusion. So all I've done is I've written exactly the same formula, but replace x by x tilde. That's all I've done. And by which x tilde? X tilde t plus 1 given t. That's the thing we have to work out. And when we do that, we're pretty much done. Okay? So how are we going to work this out? Well, in order to deal with this, first we're going to have to understand sigma here. I can see here. But it's staring us in the face right here. This is y of t plus 1 was what again? Ugh. So I've just written down y of t plus 1 here. And you can see why I can't stand the notation, but that's a standard notation in textbooks, so I'm using it. The 2 here and the 1 there bothers me. I don't like it. But that's the notation we stuck with. And now when I write down the conditional expectation of this, given estimates up to time t, measurements up to time t. Well, that's independent of past. So this is just equal to that. Okay? So what I get is c times the deviation. You don't like that?
Oh, I think you're missing a bracket, right? That's all.
No, I put the brackets here for this term here. Maybe I should use my color.
No, I mean for like x time.
Right up to T.
Oh, really? Okay. Ah! Okay.
But that's not.
Okay, good. All right. All right, so you see that we've got everything in terms of x tilde t plus 1 given t. That's nice. So we've got, we had to look at this covariance, but you see that both, this is just a function x tilde t plus 1 given t, and everything involves this measurable quantity. But come on, I was testing you. We got that too. Okay. So there's x. All right. So let's do it. So I want that. Well, you've got your notes. I have to erase it. Okay, so I just stuck a little tilde there, and you know what that means, what I just erased. Okay, so we've got to work out these quantities. Well, we now know how to work out this covariance. It's the expectation of this times its transpose. So the covariance of this term is C, covariance of that times C transpose, and then the covariance of W added on. Because this is Gaussian and independent of this, so I can add up the covariances. The covariance of the cross covariance So remember what I meant by was this. That's what we wrote down before. And we again just look at this picture over here. And thankfully, C is independent of this node. So it just involves this tree. So it's just, I get this flipped around. Because I have a C transpose here, I'll end up with this times C transpose here. And again, this new noise is independent of everything. Because I'm assuming, yes, it is. All right, so almost there. Except I dropped, no, that's right. I've got this term. So we can plug this into here. And what's that?
We need to use the inversion lemma.
Well, I know if we want a recursive algorithm, we're going to need some sort of a lemma, but I'm not going to worry about that. For a recursive algorithm, go to Wikipedia. Or something like that. Oh, but actually, here we here we don't. Well, yeah, here that's true. So in order to invert this, well, yeah, I mean, pick your favorite algorithm. If C is a rank 1, if it's a rank 1 matrix, it's a nice algorithm to invert this. Yes.
Oh, that should be T built plus 1, right?
And thank you very much. So I'm glad I saw that. So what's left? Oh, we don't have sigma. That's the only thing missing. Okay, let's do it. So some of this is easy. Maybe I've written this down. No, I haven't. Say what's sigma t plus 1 given t? I'll just write it down. We know it's a deviation term. And that's not quite right. That's right. So it's the, as we've seen before, this involves ax hat t given t, we've seen before. So this is the deviation, and then this noise here. So a relationship between sigma t plus 1 given t and sigma t given t. And then what about the next one? How are we going to do that? Well, I want to use a rule. That should be a tilde, right? God, I can't believe this isn't more transparent in my notes now, but it's better to do it this way anyway. So I've got x minus x hat. I want to write it as x minus x hat given some older information, minus x hat of t minus x hat of t minus 1. Sorry, x hat of t given t, x hat of t given t minus 1. And I'd love for you all just to look at the rules and say which rule I should apply, but the way I've written this down, it's not really that clear. But algebraically, we can do it. This is so you can do this two ways. You can just do it by brute force calculation, or you can look at rule number 3. But either one, this is equal to this. By algebra, by 1/3 of that. And that's nice because we know that this is related. This will give us a recursive formula. We have to close the loop here, right? This is the thing that looks scary at first, but let's see if we can figure this out. Where is it? So glad it's not erased. So remember, this was x hat of t plus, t plus 1 given t. And this here is some gain. Let's give it a name now. This depends on t. The new estimate is a times the old estimate times some gain times the innovation. And so we can plug that in here until those people kick us out. And what we get GT times PT. And now we get kicked out. But man, what a horrible place to stop. But this turns out to be a function to be seen. Some algebra, and you get this formula. Okay. Very, very small amount of algebra. And there it is. That's the Kalman filter. I can combine these two equations, and I get a recursive form for sigma. I mean, so that's it. I actually am going to force you to go to see a reference book because the concepts are all here. There's an algebra left out. I'm glad. So. See you next time. We're going to talk a bit more about linear theory and about why superpositions are fragile. I'll give them a bandit problem to show you. About the projects, I've gotten your tentative projects, and I really want to go through these carefully because I don't want to set you up. If your project doesn't really, build on ideas in the course, you're not going to do well. So if your title of your paper is on